Okay, so this talk is more, to be perfectly honest, is more designed for fun than to give a lot of technical details. I'm going to give you a little bit of philosophical perspective, and I just want to emphasize this is my own perspective. I've designed this talk, and this talk comes out of a paper that we currently have in review right now, and the paper and the talk are designed to be extreme, provoking. So some of this is pretty hyperbolic, and really my intention, and definitely controversial, and I'm going to say some things that are fairly offensive to quite a large group of people. And I enjoy doing that kind of thing. I'm sure that some of you out there have heard me talk before, and you know that this is how all my talks are, but and so this is kind of designed for fun more than anything. But what I'm hoping that people can get out of this sort of philosophically motivated talk is just some high-level perspectives. I'll give you a little bit of introduction to some of the work, the actual technical work we're doing here, but the details are going to be pretty small, and mostly I just want to give an overview of what I see happening in the area of machine learning in hydrology, and specifically I'm talking about surface hydrology, so mostly streamflow, but we've done a lot of this work in land surface modeling as well. Just to give a sense of my collaborators, so we have a pretty large group of people now that work sort of on a daily basis, work together on various aspects of these problems. And I would say that Freddie Kratzert at Johannes, he's a PhD student at Johannes Kepler University studying under Sepp Hochreiter, is really the driver of a lot of the work that I'm going to show, especially at the beginning of the talk. I'm currently visiting faculty at Google Research, and Google is entering into the hydrology game. They're building a flood forecasting model, and they've already produced flood forecasts for tens of millions of people over the last 2 years. And so one of the exciting things about that's going on at Google is that they already have the infrastructure set up to push their hydrologic predictions to people that actually need it. So they can do, whereas the government agencies in the United States and Europe and other places like that can do this kind of thing, Google is much better situated to provide real-time information to people. And also, one of the exciting things happening at Google is that they're not tied to the old physically based hydrology models. There's some sort of, one of the things I want to emphasize in this talk is that there's some sort of sentiment among hydrologists dating back to what we would call in hydrology called the Blue Book era, where the people coming out of civil engineering departments were trying to create space to do hydrological science rather than hydrological engineering. And that was a really interesting thing happening in the 70s and 80s and 90s in our discipline. But one of the bad effects of that effort that persists today is that sort of a preference for certain ways of thinking in the discipline that don't necessarily help us provide the best information to the world. So one of the main jobs of hydrologists is to provide information about where water is, where it's going to be, and what state it's going to be in when it gets there. And sometimes what happens now that we've been successful in sort of separating hydrological science from hydrological operations is that a lot of the science that we're doing, I don't think necessarily supports this societal relevance. So that's kind of what I want to talk about today from the perspective of machine learning. So I'm going to tell you a story that I found interesting. So, in 1900, Lord Kelvin gave a speech that's been colloquially become known as Kelvins Clouds. He gave the speech to the Royal Society, April 27th of 1900. And he said there are two clouds in physics: the failure of the Michelson-Morley experiment to detect the luminous ether and the ultraviolet paradox. Probably most of you are familiar with those things from undergraduate physics classes. And within 10 years of 1900, Albert Einstein had come along and not necessarily solved those problems, but transformed those problems into new theories. And we still have those theories today. They are general relativity and quantum mechanics. Einstein laid the foundations for those approximately 10 years after Lord Kelvin famously told the physics community that physics was all but solved, except for these two very small problems. And of course, that's not true. So in 1987, Keith Bevan, and for those of you who don't know, Keith Bevan is the most highly cited hydrologist in history. He's out of the, I believe it's University of Sheffield in Lancaster, sorry, in the UK. And so he wrote this, he gave this talk to the International Association of Hydrological Sciences in 1987, and he said there's two unsolved problems in hydrology. One is that we lack scale-relevant theories of watersheds. We don't have a way, this illustration over here on the right, we don't necessarily have a way to take what we learn from soil column experiments and scale those up to the types of heterogeneity we see in watersheds: landscape heterogeneity, vegetation heterogeneity, climate heterogeneity, both within a watershed and across watersheds. And so we don't have basically an organizing principle of watersheds. And the second thing he's found missing in the science back in 1987 was that he said these theories should be stochastic. So he wanted to, he really spent most of his career, especially after 1987, advocating that hydrologists should quantify uncertainty. And what he called for specifically in this 1987 talk was that the theory, we should develop a unifying theory of watersheds, and it should be stochastic so that it can provide estimates of uncertainty. A year before that, Jim Duke had borrowed, this is a really interesting paper that most hydrologists are aware of. It's interesting to me because Jim Duke borrowed this argument directly from Gerald Weinberg, who is a computer scientist. He even stole this image that I have on the screen from Gerald Weinberg's from Weinberg's book, 1975 book. The name's escaping me at the moment. But anyway, so the whole argument that Jim Duke was making back in 1986 about why we lack scale-relevant theories of watersheds was borrowed from a computer scientist. So I think that's especially fitting in this context. And basically what Duke said was that there are two kinds of domains where we have this unreasonable effectiveness of mathematics outcome. And these are domains where we have mechanistic laws. These are things like Newton's laws, where our students launch tennis balls down classroom hallways, and they know they can predict exactly where those tennis balls are going to hit the ground based on the force applied in the catapult. And the other kind of physical laws that work really, really well are based on laws of large numbers or ergodic theorems. And these are things like thermodynamics, where we can rely on statistical properties at large scales to make really accurate predictions of macro scale properties of systems. And what Weinberg and then Duke said is that a lot of the stuff we care about doesn't lie in the domain. So mechanistic laws work where we can keep track of every particle in the system. These are like things like planetary motion and catapult projectiles and ballistics and things like this, where we really know all of the relevant details of every individual component of the system. And the aggregate theories work where we have enough components that we don't know the details of that we can rely on large numbers. But a lot of the systems we care about, economics and hydrology in particular, live in this area of what we're going to call organized complexity, where we don't really know enough about the system to keep track of everything, and we can't really rely on the laws of large numbers to really average out all of the heterogeneity. That's why we don't have scale relevant theories of watersheds. So just to give you, bring us back up to date, this paper is up on Earth Archive, and immediately within days, Keith Bevan wrote a reply and had his replies published. You can read it in Hydrological Processes Journal. And he said, I'm paraphrasing strongly, maybe over characterizing what he said, but he said, basically, I don't believe what I said back in 1987. We shouldn't be looking for scale relevant theories of watersheds because every watershed is different. And he has a name for this concept. It's called uniqueness of place. Okay, but Keith Bevan is pretty much alone in that sentiment. The hydrological community came together in 2018 and 2019, and they came up with these 23 unsolved problems in hydrology, sort of to mimic the 23 unsolved problems in mathematics from several decades ago. And one of the problems, problem number 6, was the same thing that Keith called for in 1987. It's what are the basically what are the scale relevant theories of watersheds? Can we develop a hydrological law at the catchment scale? And how do these things change with scale? Okay. So the community is known for a long time and still talks about this, that we lack scale relevant theories of watersheds. And again, just for those of you who aren't hydrologists, watersheds are the primary object of study for almost any surface water hydrologist. And there's really sort of 3 theories in the community about why we lack the scale relevant theory of watersheds. One is this uniqueness of place, which is Keith Bevan's favorite theory, and that is that there just isn't a theory of watersheds because all watersheds are different. So there's no way that we can come up with a description of watersheds that really works across all watersheds. And we see that in our mechanistic conceptual models. Really, you only get good hydrological predictions. Again, I'm exaggerating just a little bit, but you only get really good hydrological predictions when you have lots of data in one particular catchment to calibrate your models. The second theory, or hypothesis about why we lack scale relevant theories of watersheds is that we lack data. So there's so much complexity in the watersheds, we just don't have the sensor networks. Remote sensing is only looking at this very top surface layer and only certain variables that we can detect from space or detect proxies of from space. And so we just don't have the data that would be necessary to come up with these theories. Of course, there's a third option, which is that we have enough data, the information is in the data, but we just haven't had an Einstein in our theory to come up with, in our discipline to come up with a new theory of watersheds. Okay, so this is the situation that hydrology finds itself in as of 2019. So I'm going to tell you about a few experiments that we ran with deep learning, and basically just to give you a sense, this is the data that we're using. We're using the CAMELS data set. It's 531 catchments scattered across the United States. The United States is pretty big, has a lot of climate zones, vegetation zones, different elevations, different precipitation patterns with different aridity indexes. And so we have these 531 basins. We have 30 years of daily data in each basin provided by the USGS, and we have several different meteorological forcing products that are sort of cut out for each one of these basins. The CAMELS data set comes from INCAR. There's a couple references down here. We've fed this data, basically the CAMELS data, directly into an LSTM. So this is a completely, I don't want to say non-interesting experiment, but it's just a completely rote application of deep learning. So we fed the CAMELS data set into a LSTM model, which is a time series model with a state, sort of a state space that looks a little bit vaguely and only at an intuitive level like a PDE solution. So there's a state that evolves over time in response to inputs and outputs. And we did that over the CAMELS data set, and we benchmarked it against the models that are used in the United States for operational flood forecasting. These are the National Water Model run out of the National Water Center in Tuscaloosa, Alabama, run by NOAA and USGS, and then also the Sacramento Soil Moisture Accounting Model, which is the SAXMA thing, the orange line on the plots. And this is the model that's underneath the national the river forecast, National Weather Service river forecasting centers that are used operationally in the U.S. And our model is in red. So the LSTM, just a rote application of the LSTM, is in red, and the out of sample application of the LSTM is in purple. So the problem of predicting in out of sample basins in hydrology is called PUB. That's prediction in ungauged basins. This was the decade-old problem of the International Association of Hydrological Sciences from 2003 to 2013. So it's one of the biggest and most well-known named problems in hydrology. So we created an LSTM that's trained on a bunch of basins and then used to predict on basins where it's never seen data. And we compared it against Sacramento, which is calibrated individually for every basin. So you could not use the Sacramento model effectively in a basin where you didn't have long data records. And the National Water Model, which is a mix of calibrated basins and uncalibrated basins. And the thing to point out here is that the LSTM, just deep learning, does better in the PUB setting, in the ungauged basin setting on average. This is the Nash-Sutcliffe efficiency, which is basically an R-squared. Scored higher is better. These are the sort of smooth kernel histograms over the 531 basins. So you really want these peaks to be as far to the right as possible. These are the corresponding CDF plots. And basically what we see is that just out of the box, deep learning in purple does better in ungauged basins than basically the best hydrology models in existence do when you in the perfect situation where they can be applied. So the SAXMA has been around since the 60s. It's the most widely used hydrology model in the world, almost without question. It's almost always, not always, but very often, it's the best hydrology model in the world when people do benchmarking. And it only works really in basins where you can calibrate it, and the LSTM out of the box does better in basins where it's not calibrated. Okay, so that's just establishes a baseline of what we're talking about. One of the interesting things about the LSTMs is they actually do better when you train one model for all the basins rather than training a separate model for each basin. And this is revolutionary in hydrology. There is no existing hydrology model that behaves like this. This has been a goal of the hydrological sciences for the greater part, for longer than half of a century, and we have not. The community has not been able to build something that operates like this. It's called regional modeling. It's an area of study in hydrology, building models that can be calibrated in some basins and used regionally. And LSTM does this better. So you want to be as far to the right on the CDF plot as possible. And the LSTM that's a single model calibrated at all the basins. So a regional model is in the dark, the solid line, and the model that's the LSTM calibrated at each individual basin is in the dotted line. And so really what this is saying is that the LSTM is able to learn even though there's diversity of catchments out in the world and there's diversity of rainfall runoff processes in its catchments, the LSTM is able to learn some similarity between the catchments. It's able to see catchments in Texas and by looking at that data, help it improve its representation of hydrological behaviors in catchments up in Michigan, for example. And that's even if it sees data from catchments in Michigan. So it's really able to learn something fundamental about hydrology and transfer that between basins. There's a really nice paper on arXiv by Martin Ghosh, who's was a master's student up in Waterloo, now a PhD student at Johannes Kepler out in Vienna. And he sort of split the data up in different ways and looked at how much you gain by training on multiple basins. And again, this is a fundamental step change in hydrological prediction. This has been the goal, sort of, I would say, probably the largest goal of hydrological modeling in the last half century. And it's the first time that we've seen evidence that this is happening. So how is the model doing this? We have a technical paper on this down here that you can read. I just want to give a sense that what we can do is we can break apart the LSTM, we can pull out certain feature layers, we can arrange the LSTM in certain ways so that the feature layers are frozen, and we can pull out, this is just a feature, one of the input gates to the the set of input gates to the LSTM. We had 256 input gates, 531 basins, and this is sort of the activation, this is the level of activation of each one of the gates for each one of the basins. So and this is sigmoid activation in the LSTM, and so this is a number between 0 and 1. 1 means that more information is flowing through that gate. 0 means that less information is flowing through that gate in this particular way of viewing the feature layer. And so basically what happens is that each catchment has a fingerprint in terms of how information is moving from the inputs to the states of the LSTM. This is like the rainfall state relationship in a traditional hydrology model. And we can just kind of see that the model is learning to group catchments together. And so the catchments are vaguely organized from the East Coast, it's backwards. East Coast over here at 0, vaguely to the West Coast over here at 531. It has no spatial information, so it doesn't know that two catchments are close together in space, but yet it kind of sees regional similarities across the United States. You can just kind of see bands in here where it says catchments that are close together are kind of similar. And again, it has no idea. So it has no idea that catchments of how close or related each of these catchments are, except for the properties that we give it, describing the catchments, which are things like climate and vegetation, stuff that we can mostly see from space. Yeah, so what does this tell us about the problem, the unsolved problem in hydrology? The unsolved problem being that we lack sort of biogeophysical theories of watersheds. And what it tells us is that really this is because the hydrological community just simply hasn't developed those theories. So it's not that that machine learning provides those theories. It's not that machine learning says that there's enough information in the data that we could, you know, solve this problem to the precision of experiments that we see in quantum mechanics. But what it's saying is that there is significantly more information in the data than hydrologists have been able to pull out just by sitting down and thinking really hard. And that step change in the amount of information that's we're able to pull out of data versus what hydrological theoreticians have been able to describe is large enough that it allows us to really attack some of the central problems in the discipline, okay? And I think that's important because it means that when we talk about knowledge-guided machine learning, in this particular case, rainfall runoff modeling, my argument is that maybe the goal isn't to put knowledge into the machine learning algorithms, maybe it's to get knowledge out of the machine learning algorithms. And this is not a sort of a unique observation. We've known for a long time. Here's a list of papers that look at this problem in the land surface community. This is some results that I don't really want to take the time to describe, but just the intuition behind this is that we have these benchmarking exercises. We've had them for many, many years, going back at least a decade and a half, against almost all of the hydrological fluxes and states and fluxes that we really care about: evapotranspiration, radiation balances, carbon balances, net ecosystem exchange, soil moisture, where machine learning basically produces results that are better than our models all the time. And that's fine, machine learning does well, but what that's really saying is that there's extra information in the data. So I want to make a contrast between this situation and the kind of situation that we were seeing sort of maybe in some of the early talks yesterday, where we're worried about limited data and we're worried about using physics to sort of deal with the fact that we can't observe everything or we might have limited data. So what's happening in streamflow hydrology is that we have a lot of data and a lot of information in the data, and the challenge is really extracting that information in ways that are interesting. And yeah, and so one of the symptoms of this, I would say, is that, you know, I review a lot of machine learning papers in hydrology, and often we get papers where people break the machine learning models intentionally, like they do data denial experiments, things that are kind of semi-legitimate. But what they're saying is that if we put physics into the model, we could do more with less data. And that's okay, but it's not really that interesting because we're never going to have less data than we have about some of these fundamental problems in hydrology: drought monitoring, soil moisture drought monitoring, surface flux estimation, ET estimation, and streamflow estimation. I mean, the point is we have all this data. We already know that it's enough to do more than we could do with theory. And the question isn't now sort of how to put the theory that we have into the models. It's how to learn, it's how to use the models to learn both about what parts of our theory may be useful for regularizing. I mean, we still have this problem of non-stationarity going into the future. So there may be some parts of the theory that are useful for regularizing that problem, but certainly we wouldn't want to keep all the hydrological theory because a lot of it's actually hurting us. These colored bars, the high set of color bars in each of these figures are the amount of information extracted from machine learning models. The low set are the amount of extracted from the hydrology models. And so we certainly don't want to keep all of the hydrological theory. So certainly the future of hydrological science looks more like dropping theory that we think we know than it does, and maybe learning new theory from machine learning than it does necessarily taking the theory that we have and trying to use it in a machine learning context. We've tried to do that in many ways. So in the few minutes that I have left, I'll just give you a very brief overview of what that looks like. The easiest thing to do, of course, is to take the output of a physically based model and plug it into a machine learning model. So we've done that extensively, both with the National Water Model and with the Sacramento model. And the answer is that you don't gain anything. We're by post-processing, we call it post-processing. That's where you take the output of the National Water Model and feed it into the LSTM along with all the other regular data. And we improve over the National Water Model a lot. There's a lot of room to improve over the hydrology models, but we don't really ever consistently improve over the deep learning models, just the raw, straight up deep learning models with no physical information. I mean, some catchment, and there's a little sort of a scatter about where we do better or worse, but on average, the CDF curves are directly overlapping. And that's true for every hydrological model, every state in flux that we've tested so far. Deep learning lets us use the data that we have in more easily and more effectively. So not only do we get more information out of the data we have, it's actually much easier to use this. So this is an example of assimilating remote sensing data into directly into some of our streamflow models. This example comes from Alden Sampson at Upstream Tech, which is the only company that I know of in the world that's actually producing these LSTM-based streamflow predictions to sell to customers. Alden's model is the best existing hydrology model in the world, just to be very clear about that. But so Alden decided he wanted to bring data simulation in, and just to give a sense, like to bring remote sensing data into his models, and just to give a sense, if you want to do that with a traditional hydrology model, you pretty much have to use data simulation. And to set up an effective data simulation system is many, many months of person time at minimum. Alden was able to sort of produce this plot in an afternoon, basically just by training his model with new inputs. And sometimes you can't do that, like immediately after you launch a satellite, there may not be enough training data, but the methods for doing traditional inverse data simulation that look like Kalman filters and the things that the hydrology community uses in deep learning models is actually much easier and more effective in deep learning models because you already have these backpropagation gradient chains in the tensor network. So you can do data simulation. You can bring in the satellite data without doing data simulation. And if for some reason you want to simulate, like a new satellite is launched and you want to simulate from day one, maybe not day one, but at least 1 month in, you can train a new head layer on your deep learning model to predict what the satellite is seeing. And since that can be a simple linear head layer, so you don't need really any data to do that. And then you can start assimilating immediately by actually pushing the updates back through the backpropagation chain. So these are really, really hard problems in hydrology become very, very simple in terms of extracting more information from data. So how do we add physics? Adding data is pretty easy. How do we add physics? And there's sort of a whole bunch of ways that people have talked about how to add physics. The one that I'm most excited, so a couple that I'm excited about are system identification, which is where we take a whole physics model. We add little machine learning kernels to the time series component. It's a PDE solution. It's discretized in space or time, and you can add a little machine learning or learning kernel to the numerical solution, and you can actually learn nonlinearities that aren't present in whatever numerical solver you're going to use, or whatever description of the system equation PDE that aren't even in the PDEs that you're going to use, let alone the numerical solver. And the other one that's really interesting to me are embedding architectural symmetries into deep learning networks. So it's actually pretty trivial to embed conservation laws in deep learning networks. You can just force the network to have certain symmetry properties. And that lets you do things like avoid regularized loss functions, which are finicky because they aren't exact. There's sort of some margin for error, but you can actually construct deep learning networks in a fairly trivial ways that architecturally enforce symmetry, so that no matter what your loss function, you can train to any loss function you want. And that's a valuable property because different users of hydrological models have different objectives, and you want the loss function that you trained against to match the objective of the user of your model. And so you can avoid putting the physics in the loss function by just having a deep learning model that, for example, doesn't violate conservation of mass. So these are the kinds of things that we're thinking about. And really where I want to go with this is this unanswered question down at the bottom, which is right now we're getting much more value from machine learning and directly from data than from anything the hydrology community has done in the last 100 years. In fact, we've spent years trying to embed pieces of physics into these hydrology models, and the models that we're actually running for customers don't have any hydrology in them. And it's not for lack of trying, it's because every time we added some type of process understanding in one of these ways that's listed on the screen and many others, it's hurt the prediction. So we have not yet, after several years of really putting a lot of effort into trying, we have not yet found any way to improve streamflow predictions by bringing hydrological knowledge into the system. Just zero. Beyond literally the only hydrological knowledge in the world's best hydrology models, streamflow models right now, is that rainfall turns into streamflow and not the other way around. There are papers that show value in the community of putting physics into streamflow models, but they're not benchmarking against state-of-the-art deep learning models. They're benchmarking against rather inelegant proxies of what's actually happening in the companies and the agencies that are actually doing streamflow deep learning in a serious way. Okay, so what does it look like to put physics into an existing hydrology or machine learning into existing hydrology model? One of the simplest ways to do it is like this. We have a ODE or a PDE of some form, and this F is just our process model, whatever that model may be. Maybe it's the NOAA-MP model that's being used in the National Water Model. Maybe it's SUMA. Maybe it's some other hydrology model. We add a machine learning kernel, and we expect this kernel to help us learn the state update. So how X is the state of the system, that's the storage state, usually other types of variables other than storage variables. And we can sort of update, we can sort of adjust the way this PD or this ODE evolves in time by learning a new term in the equation. And we can even learn stochastic terms. So again, any type of probabilistic deep learning can work here. Gaussian processes is what we're using because we really like the fact that Gaussian processes revert to a zero mean prior outside of the range of observations. So what that means is that if we go outside of the range of any data we've seen before, we revert back to the physics-based model. So we like GPs for that reason, but any probabilistic neural network, mixture density networks, CMOL networks, Monte Carlo dropout networks, anything can be used here to add stochasticity to this, to turn this into a stochastic partial differential equation. The problem is that training the machine learning model on the inside of a PD solution like this is non-trivial because we usually don't fully observe the state of the system that we're trying to evolve in time. So it's a latent variable problem, and it's a pretty nasty latent variable problem because the latent variable is actually the training data for whatever machine learning kernel we're trying to use. And so there are ways to solve this. Shubin-Girmani published the first one that I'm aware of back in 1999 and 2000, where he just used a Kalman filter as the expectation step in an expectation maximization algorithm. So he treats the training data or the states as a latent variable. He gets a first guess just from the process model. There's some sort of Bayesian approximation. A Kalman filter is an example of a Bayesian approximation to sort of integrate over the uncertain, the possible state space. You come up with an expected value of that integration based on complete zero mean prior on the Gaussian process, for example, basically just using the physics model. Then you train the Gaussian process or whatever machine learning kernel you're using here. You train that on the expected state value from your Bayesian update. That's a maximization step. You're maximizing the hyperparameters of the machine learning model, and then you do the expectation step again and the maximization step again. And there's several papers that show try to show how closely this approximates a true expectation maximization procedure. It would be an exact expectation maximization procedure if the data assimilation were perfect, but usually for this type of highly nonlinear system, we have to use ensemble data assimilation, and there's no sort of theorems that guarantee convergence of Bayesian approximations under ensemble sampling for a variety of very well-known reasons. So it's an approximation of an expectation maximization method is one way to do it. There's many other ways to do it. There's inducing point methods. There are variational methods. There are other types of Bayesian methods. But basically, we're using something that's familiar to hydrologists, which is this expectation maximization step, where the expectation is data assimilation, the maximization is backpropagation, or whatever we're using to train. In our case, it's not backpropagation, it's training the Gaussian processes. We apply it to streamflow models and we get lots of value. So we'll look at this plot over on the right. The better models have a lower mean squared error. The model alone in a 3-year out of sample period, that's the forecasting period, a 3-year observation period, that's the simulation period. The model does pretty similarly on both periods with no data. Then we do parameter estimation. Of course, the model improves more in the period in the training period than in the test period. And then we do data assimilation. Data assimilation doesn't provide any value when there's no observations because it's just updating the state of the model in real time, but it provides a lot of value to a streamflow model, as the community well knows. This is a Kalman filter type thing. And when you have observations, and the goal is to sort of store that value in the structure of the model. And we do that by learning this GP term with expectation maximization. So we can store a lot of the information we get from data assimilation into the structure of the model, and we can go for long periods of simulation, so 3 years out. So this is more like, this is taking information from observation data and using it at seasonal to even maybe even climate timescale. So not just making one day ahead improvements to prediction, which is what you would get from data assimilation, but making long-term improvements to our hydrological forecasts. We applied this to the NASA Land Information System and the soil moisture state using FluxNet data, and basically we see improvements almost everywhere. It's sometimes the GP, because of GPs aren't great. I really don't like GPs in particular. They're highly unstable. They're not easy to work with. They're not easy to scale. We have an HPC GP code, if anybody's interested in using it, that uses sparse and also non-sparse matrix inversion that can be run on GPUs and CPUs, and that helps us train a little bit faster, but GPUs are just really slow, they're really finicky, and so sometimes they go off the rails, and there's a few sites where that happened, but overall, on the FluxNet data using the NASA Land Information System, where we're trying to predict soil moisture, this improves the predictions of soil moisture by a lot in a lot of places. We're getting sometimes 80% reduction in the prediction of soil moisture, and so what we're really seeing here is that if we're really getting 80% reduction in the error in our soil moisture predictions, what we're learning is that a lot of the error originally is not coming from bad forcing data, it's coming from bad models, and so there's a lot of room to improve these hydrological models.
Great. We got several questions that have come up, and it's nearly the end, so if you could finish up.
Yeah, we'll just stop there. I'll say one more thing and we'll stop. I didn't really prepare to talk about this a lot, but you can embed conservation laws into neural networks. It's actually a trivial problem. It's not even interesting to talk about really. And basically all that is that you L1 norm the output from a bunch of output nodes anywhere in your model that you want, and you multiply those normed outputs by a conserved quantity. And if you do this anywhere in your model, you can track conservation through your model. So you can have a deep model, and you can place these L1 normed layer, these normalization layers that normalize and multiply by a quantity that you want to conserve. You can do that anywhere you want in any type of deep learning model. And if you do it at least once in the output, in the head layer, you get a model that obeys conservation principles. And that's really easy to do in feed-forward networks. It's a little harder to do in time series networks, but it's really easy. You just replace all of the gates in an LSTM with this, or at least add this type of conservation normalization to all the gates in the LSTM. And so when people talk about deep learning being black boxes or not obeying conservation principles, these are, I would go so far as to say these aren't even interesting problems to solve. They're just sort of trivial things that we just haven't really done a whole lot of. And I'll just leave it at that. Thanks.
Thank you for that excellent presentation, Gray. We have several questions. We won't get to them all because I do want to keep on time here. But the first one is, which characteristics do you find similarities in the catchments?
Yeah. So we have that in our paper. This is sort of my favorite plot that shows that we look at that several ways in our paper. You can get the reference from Google Scholar or from these slides. This is my favorite plot. It depends on how you ask the question. So I don't see the exact wording of the question, but the exact wording of the question can change that answer. The ordering of the importance of the different inputs can change it almost exactly. So it's whether or not and the difference is whether or not which is like, we can look at the gradients and see which inputs the model's most sensitive to, and those are not the same as if we look at what the feature layer and then try to extract information from the feature layer through dimensionality reduction. And I like the dimensionality reduction way because we're letting the model learn, and then we're trying to understand what it tells us rather than trying to understand how the model interprets what we give it. So I just suggest read the paper, and that the answer to that's pretty subtle. But in terms of extracting information from this trained feature layer, the clustering that we see in this feature layer is driven by vegetation and the seasonality of vegetation.
I think that, thank you, Gray. We have other questions. I'm hope we'll be able to address them in the panel session at the end of this. So